All right, I think one more person came in. So let's get started. This is week 7. We're almost there, 8 weeks, and this class will be over. And next week, you guys have the symposium to look forward to. We'll start off today as we usually do, just a time where I can review any issues you had. So whether that's with the drivetrain, with the assembly, any part of the project, if you have any questions or problems, you can bring them up now. All right, so is everything going well for everyone? Seems like it. Okay. So as before, I'll try to keep the next part a bit brief, but what we're going to be talking about is kind of mechanics of materials, a bit of statics. And so this will be relevant to you if you're on like robotics team and you have to design something yourself. And a very common question that you probably thought to yourself at least is, how do I know that if I make this in real life, it won't break? So a lot of how you decide that goes into like what you make things out of, a lot of the common materials you'll use. Some of the things we've seen, like the CE channels, the U channels, are probably made out of steel. All of your hardware and stuff, like bolts and nuts, are almost always steel. Things like A20 beams and other, like maybe custom machined components, will probably be made out of aluminum. Some of you might work with wood, which is pretty common, especially in like when you're first learning to use the shop. And it's pretty cheap and widely available material. And for 3D printing, two of the most common materials that we've talked about before, and you may have seen before, are PLA and ABS, which are types of plastic. And so these are kind of the palette that you have to work with when you decide what you're going to design. And of these materials, I just want you to take a moment to think about each one and ask yourself what properties of materials we care about. And so in a moment, like if you can name just a property of a material, maybe in your science classes, you've talked about these, you can type in the chat or unmute and speak up. And when we talk about properties, it doesn't have to be anything like very technical. Just what are some properties, some characteristics, what makes materials different from each other? Okay, so one person says weight, which is very true. Like these different materials have different densities, which means that for the same like sized object, you might get a different weight. Maybe one more. Okay, size, that also ties into it. So not only do materials, like certain objects, have their size, of course, but depending on like say strength, which is another property, you might have to make some things bigger. Like you can make a lot smaller objects out of steel because steel is stronger compared to something like aluminum or wood. So those are two. There are lots of other ones, but what we're going to talk about today is kind of strength. So there are a few like vocabulary type words that you'll probably run into if you study like physics or material properties. Don't worry too much about like the Greek symbols or the equations. Those are just like other names for it, but they're just these concepts that it's good to have an idea of, because as you analyze things for robotics teams, you're probably going to care a little bit about these concepts. So the first one we're going to talk about is stress. And so stress is a very common word that we talk about ourselves as well. Like I'm very stressed today because I have all this work to do. And similarly, materials can experience stress. And what we mean when we talk about stress is kind of similar to what a person, if you have like a lot of stuff to do, there's a lot of pressure being put onto you, that'll make you stressed. And we define stress like for material, literally it is defined as like the force per unit area. Those are the dimensions. So if you remember, we talked about simple machines. Force is kind of like the ability to move things, the ability to do some kind of work. So any kind of pushing is kind of a force. And so the per unit area means how focused that force is. So in general, it'll kind of be related to like how hard you're pressing on material. And that makes sense. If you really push on a material very hard, it puts a lot of stress on it, as opposed to if I just put a small force on it, there's not a whole lot of stress going through the material. So there are a lot of different types of stress that a thing can see. And as you design things, one thing you'll want to eventually start keeping in mind is what kind of stress will this object that I'm modeling see. So some of the straightforward ones you might have heard before, it's like tension is the ability, like tension is the stress that you see when you pull things apart. And opposite of that is compression, where you're trying to push things together or into itself. And so you may have heard things like cables are really good at tension, concrete is really good in compression. And so those are material properties that can inform how you design things and what you eventually make the thing that you design out of. Strain is a bit more abstract. It's also a common like word that you kind of see in English, but the meaning might be a bit more disconnected. And so the simplest way to think about strain is a change in length compared to its original length. So if I have a really long object, like my pencil, somewhat long, I guess, and you can imagine that if I really pulled on it very, very hard, the pencil might get just a little bit longer as the material deforms. And so that tiny, tiny bit of length change, it's so small that you might not be able to see it, but you can imagine if I pulled on this really hard, it might stretch a tiny bit. And so the ratio of how much that material can stretch out in length over its original length kind of describes the strain that the object has experienced. And so this can be caused not only by like pulling on it really hard, like not just stress, but also if you heat things up. You may have heard about like thermal expansion before. Things tend to get bigger when you heat them up. So that also causes strain. And so you can just think about it very simply as the change in length. And so these two quantities are kind of related to each other, as I just mentioned with this analogy. If you really pull things apart, they kind of experience strain because they get longer. And so that behavior is what we're going to talk about next. This equation is kind of like the mathematical way to relate them, but it's not something you have to worry about too much. Just know that there's very literally a linear proportion between the stress and the strain. So what we'll talk about next is this kind of stress strain curve. So many of you have probably seen like graphs of functions before. So here in the x-axis, we have stress. That's how hard we have strain on the x-axis. On the y-axis, we have stress. So as you follow this curve, this entire curve kind of describes one single material. And so this particular one probably describes some kind of metal. And the way you interpret this is as you kind of go up the y-axis, you follow the curve and you can see the stress is increasing. And as the stress increases, how far horizontally it goes shows you how much the material will deflect. And so what you'll see happen here is at the very beginning, when you're just putting in a small amount of stress, the amount of strain that you get, the amount of length that changes is linear. So if I put in a tiny bit more amount of stress, I get a certain amount of strain. If I put in a tiny bit more amount of stress, I get that much more strain when I'm in this region. And so this is called the elastic region because materials kind of behave kind of like a spring when this in this region. So if I have a piece of metal, you don't usually think about metal as being something that bends a lot or easily, but at a very small scale, if you apply force to a metal or any object that's elastic, it'll get longer a tiny bit. And when you let go, it'll kind of spring back into its original shape. So that's what happens in this first region. And then when you reach a certain amount of stress, you may have experienced this before with like a paper clip. If you kind of bend it just a tiny bit, the paper clip will spring back to its original shape. But if you bend it too much, then the paper clip won't go back to its original shape. It'll keep the new shape. And that's kind of what the yield strength refers to. And when we analyze materials, that's kind of what we care about, because if something happens to our robot that we design, it hits a wall really hard or it gets dropped, we want it to be able to spring back kind of into its original shape. So we want to make sure that it never reaches its yield strength. That's kind of the main takeaway for this graph. I won't get into these other sections unless you're really curious, but just remember that we kind of wanted to design our parts so that if they ever take any impacts, they'll still be able to kind of spring back to their original shape, like a paper clip that only experienced a small deflection. So knowing about these concepts and stress and strain in general is pretty useful, like I said, for material selection. It might decide whether or not you use PLA or ABS, depending on which one is stronger. It might affect how you design geometry. It can help you pick your hardware. Like maybe you think you can get away with using a very, very skinny bolt, but you're also afraid that the bolt might break. So how do you determine the thinnest bolt that you can use? And so doing the analysis of the stress in the bolt is a way to do that. And one last thing is kind of, you can determine a factor of safety. So once you design your robot and completely make the thing, you can tell someone, oh, for the applications that this robot will be used in, there's a factor of safety of, let's say, 2. So the worst thing that we imagine could happen to this robot is only going to be halfway towards making it yield. Later on, if you get very involved in kind of certain robotics teams or later on other projects that you do, you'll eventually come across FEA, which I briefly talked about in CAD 2 class. And so all of these statics equations, using equations kind of like this one and many, many others, the computer can solve it for you. And I guess the high level concept to take away is that you put in your geometry. So you make a CAD model. In this case, I made a CAD model of like a rectangle here. And what the computer does is it turns your CAD model into a bunch of tiny little blocks. And then for each of these blocks, it solves a whole bunch of equations, and then it tells you exactly how that block is going to deform when you put in a certain force and what the maximum stress that it will see at every one of these little blocks. So it's a very useful tool. There are some free ones out there. I think Fusion 360, the student edition, has some free FEA packages. And if your school sponsors you some other CAD packages like SolidWorks or I'm sure there are other like packages out there. You can do your own FEA of these CAD models that you make. So that's pretty much it for the lecture part. I tried to keep it a bit short. So if you have any questions about any of these concepts of stress and strain, some of the applications or FEA, you can ask about that right now. And if there are no questions, you can always feel free to ask later. I'll talk about kind of what our plan is for next week, class 8, which is the last class of this session. And so as we mentioned several times before, we're going to have a kind of symposium so that every student can show off their robot. And so what we have in mind right now is kind of for each student to prepare a very short presentation. We'll say no more than 3 minutes, but depending on your preferences, that can be like as short as like a minute, maybe if you have enough time, maybe longer. But that's the order that you should shoot for, somewhere around 3 minutes or less. And you can kind of do with it what you want. This is your project. This is your presentation, so to speak. So you can prepare a slideshow. You can just prepare some images that you want to show the class, or you can even just like share your screen in Onshape and kind of walk us through your CAD, or any combination of those things. But each one of you will just get your own like block of time to show what you've done to the rest of the class and to the instructors. And I think it'll be a good way to celebrate what you've done and kind of see what everyone else in the class has been doing for the past 7 weeks. Also, it'll be great practice because as you work on your robotics teams, as you work on other engineering projects, you're going to have to present kind of what your work has been to other people. And so it's a kind of safe, grade-free, judgment-free environment to do that. And so that is our plan. If you have any questions about this specific slide, if you have questions about what we're going to do next week, about what you're expected, feel free to ask. All right, so everyone's clear on what they need to make, what they need to do. When we meet again next week, you'll all be prepared because there are no questions right now. All right, sounds good. At any time, if you have questions, you're more than welcome to just chat or speak up or anything, and I'll address those. So that was an explanation of how this class is going to wrap up. Kind of, I guess, telling you in advance for next week, the assignment will be just to finish up your CAD for every system that you haven't completed yet. I know from the survey that I took, I think last week, that a fair number of you, maybe like 6 of you, were done with at least the arm and potentially the chassis as well. Hopefully by now you've made some good progress on assembling. I know like maybe 2 people were nearly done last week, so hopefully everyone's in a good place. If you're not and you want to talk about what you should do, you can also feel free to type about that in the chat. Hopefully the chat is open. Yeah, you can just like direct message me too if you want to keep that private. So like I said, you can prepare slides, maybe think about what you want to say, like what was an interesting feature about your design, or something that you learned during the CAD process. As I've stated a couple times, next week is our final class, so there's nothing else after that. So that's the end. Make of it what you will, and get ready for your presentations. Alex, do you have a question?
Yeah, do we all have to present?
Yes. I would say I expect every student in the class to present. It's not.
Oh, okay, but wait, we have to make, do we have to like make actual slides for our presentation, or do we just show our model?
Yeah, like I said earlier, it's kind of your choice. The whole project has been kind of your own direction of what you want to do. And like I said on this slide, you can make a slideshow, you can just prepare a few images, you can screen share, Onshape, any combination of those things. Whatever you feel would best represent the work that you've done throughout this class to your peers.
Okay, thank you.
Yep. Thanks for asking a question. If anyone else has any other things to say. And if not, I'll go into some other demonstrations in Onshape. Yeah, seems like you know what you're doing. So for the rest of the class, as we've been doing before, it's kind of your time to work on the project, get some CAD done. In the background, I'll be doing some demonstrations, which you can watch or follow along or not as you choose. Just make sure to prepare, mostly to finish your CAD and to prepare what you're going to do next week. If there are any requests for demonstrations, I asked this last time, didn't get many replies, but if you've thought about it for a while and there's something particular in Onshape that you'd like to see done, feel free to ask and I'll try my best. Um, I see someone has a question, but I can probably address that in the chat. So actually, this probably applies to most people, so I'll just anonymously address it, which is, so the student asks, to be clear, are we expected to be done with everything by next class? I've been talking about that with Jack. I think you should be prepared to have everything done by next class as usual. If you weren't able to quite finish everything, we'll give you a bit of time at the beginning of class just to polish up your presentations and like CAD. Like it's very possible that you might run into like a problem that you can't resolve on your own between this week and next week. And so at the beginning, we'll have some time like we usually do on the first slide, just like answer some questions, like address any issues. But after that, for most of the class, you should be ready to go, barring any like conceptual or I guess execution level problems. So I guess perhaps that was a long-winded answer. The short of it is, yes, be done by next class, but if you have any problems, don't worry too much because we'll help you out with that. All right, so I'll start with the demos now. This one's kind of, the purpose of this one, I guess, is to teach you one of these solid tools that you may or may not have used before. And perhaps it may be applicable to you if you're pretty much done with your robot and you just want to make it look nicer. And so at this point, the robot you have might look a bit like naked. It doesn't, like everything is showing, the gearboxes, the motors, the frame, and perhaps you don't want that. Like there could be many reasons. Maybe you don't want other teams to see the internals of your robot. Maybe you just want to protect it from like debris and dust. So what we're going to try to design for the robot today is kind of a chassis, or not really a chassis, but a kind of panel to put over your robot, just so it's covered. So like most products that you interface with, like your phone, have this case around it so that you can't really see what's going on inside, but it's much more like ergonomic. It looks nicer. And so that's kind of the motivation for what we're doing. And so as you might recall, the demonstration robot was kind of a big rectangle with 4 wheels on it. And inside there's like an arm at the center and some other like gearboxes and stuff. So what I'm thinking right now is I'm just gonna have perhaps a large piece of sheet metal that's kind of bent in a domed or curved shape, just to cover everything up and give it a bit of a shell, like a turtle, perhaps. I think from my memory, the dimensions for the sample were something like 14 inches by 24 inches. So I just sketched this onto a top plane, and this is kind of like the bottom of this shell that can just sit on top of the robot frame as it is. And I guess this is something you may not have used this before, but if you go to Onshape, Solid Tools, or 3D Tools, I suppose, you can click this little drop-down menu. The default probably says plane here. And what we want to do is make a plane. You can also just click plane there. And we sort of have talked about references before, but we may not have like really used them before. And so something that's very useful in CAD is what's called a reference geometry. So you kind of already have like fundamentally these 4 reference geometries. So the origin, the top, the front, and the right plane. And so these exist in your CAD, but they aren't actually like solid things that you get out of your CAD. Like you're never going to 3D print a right plane out of Onshape, and it's not really part of the model. And yet you probably can't CAD if you didn't have these, because you need to define all of your sketches relative to some kind of reference. And so by default, you get these 4 references, the origin and these 3 orthogonal planes. And what you can do is, using this plane feature, you can create your own reference geometry. So just like these planes, it's not going to be like part of your part. It's not going to be like a real object, but you can use it to kind of define where your other things are located, like other sketches. So let's say for this, like maybe I want a 6-inch tall shell. And so if I wanted to draw something like exactly 6 inches above this rectangle that I drew, I wouldn't have a great way to do that because sketches need to be put onto some kind of plane or a surface of a part. But right now I don't have any of those things. So what I did was I created my own plane. And the way this works is the first thing is an entity. So there are several ways that you can define planes. the simplest way is to just pick another plane and determine an offset. And that just creates another plane. That's this right here, called plane 1. That is parallel to the entity that you selected and a certain distance away. So I'm happy with that. Some other ways to make planes in most CAD programs, there's midplane, where if you have a solid object, like some kind of rectangular prism, if you pick 2 parallel faces of that object, then you can have it create a reference plane for you that's directly in the middle of those. Some other ways that are commonly found in CAD programs is like an edge, where you can select an edge that the plane goes through and kind of determine like the angle that you want your reference plane. And so these are very useful when you want to create a sketch on something that doesn't really exist yet. So I'll create a new sketch and I'll do it right on that new plane that I created. You can see it's kind of like hovering 6 inches above my top plane. And what I'll do is, for this kind of shell that I'm building for my robot, the problem with my robot is I have this big arm sticking out the middle. And so any shell that I put over the robot kind of needs to be able to accommodate that. And so I'll try to put like this circular hole in it. And what I can do, you've probably seen me do this before, just to reiterate, if you want to put something in the center of a rectangle that already exists, a neat tool that Onshape has, if you just hover a line, it'll bring out the midpoint for you. So you can just select the midpoint, select the center of your circle in this case, and you can just make it vertical. Do the same thing here and here. Make it horizontal. And you can see these points turn black because they're fully defined by this sketch that I drew earlier. And this point in the middle turned black because now it's fully defined by those 2 constraints. Then I simply give a dimension. Let's say maybe I want 4 inches just so the arm can stick out the top of this shell. In reality, I'd probably want maybe some slots so that I have more freedom to move around, but this is mostly just to demonstrate a tool that you have access to in Onshape that we haven't talked about. So what we have now is kind of cool. We have a sketch of a circle and it's kind of floating above the sketch of a rectangle. And what we'll use now is called this loft tool. And what loft basically does is it takes 2 contours. So this rectangle is a contour and the circle is a contour, and it kind of connects them together. So I'll go back to this tool in a moment, but just to show you what like the default does, it creates a solid object, and on the bottom it has that rectangle, and on the top it has that circle. And so if you wanted to just CAD this, it might be a bit of a challenge because you have all these weird curves that are transitioning from a circle to a flat line. But with the loft tool, I'm able to pretty easily create something like this. One thing I could do here, I have a solid object now. And so in our CAD 2 class, in one of the first days, we looked at the shell tool. And so if you wanted to turn this into kind of like a sheet metal type of thing, you could take that solid body and just like shell it out. So now you can see it's like a thin material. And then to create this hole for the arm to stick out of, I could just sketch a circle here and extrude cut it. And then I would have pretty much the shape that I want. Another thing that I could do, we have solids here, and everything we've worked with up to now pretty much has been a solid, but there's also a surface option. And so in most CAD programs, every CAD program is a little bit different when it comes to surfacing. Some are very powerful, some are less powerful, but I'll let it speak for itself, I suppose, to begin with. So at first glance, it seems to be doing pretty much the same thing. But when I accept it, you'll notice that it's extremely thin. And in fact, it has 0 thickness. And so that's kind of what a surface is. To put it very like fundamentally, a surface is kind of another type of reference geometry, like the planes that I talked about. So these things can be used kind of as a reference for other things that you make. This isn't a real object that I have, even though it's gray and shaded like a body is. This isn't something that you could 3D print because it has no volume. It's just infinitely thin surfaces that kind of make up this geometric shape. And so you might be wondering, like, what's this useful for? The first, I guess, most useful in our case here is that given a surface like this one, what you can do is thicken. And that kind of does exactly what you think it does. If you select these faces, it'll make it thicker, maybe an 1/8 inch thick. And now, instead of just having that surface, I now have a part. So I now have like this 3-dimensional real object. Let me hide the surface. This is something that you could, well, it might be annoying to 3D print, but you could 3D print it. This is something that if you had in real life, you could hold in your hand. It has thickness, it has volume, it has weight, it has everything. And so that's just one of the applications of surfacing tools. As you get into more advanced CAD, you'll find yourself using a lot of reference geometry and surfacing tools. So that was just kind of a taste of something you can do. You can imagine that if you had to do this with like traditional extruding and sketching, it would be quite cumbersome and you probably couldn't get these curves as nice. Those of you who are more perfectionist, maybe, may have noticed these lines aren't really like radially symmetric, or perhaps they are. You'll notice that this doesn't look that great. What you can do is in the loft feature, there are these things called guides. And so if you were to make another like sketch with a line that exactly goes from the point on the circle to the rectangle where you want this like curve feature to follow, then you can kind of explicitly force it to do something. This is just kind of what it came up with on its own. But for my purposes, it's not like I'm going to 3D print this. It'll probably be something that I make out of sheet metal or plastic or maybe even rubber. So I don't care too much. I just want to have like a model of something. And so this is something I could just stick over my robot. The arm goes through the middle and everything is now hidden from view. If you have any questions about surfaces or reference features, you can ask them. And if not, I'll go into another demonstration. All right, hopefully everyone's good with that. The next thing I'll talk about is subassemblies. So many of you have probably run into this before if you have been working on different parts of your robot in different documents. So right now this is a single document. In all my tabs below is everything that I have. So right now I just have that thing that I made. But let's say that I was working on my chassis and arm in a different document, and I started a new document to work on my drivetrain. Then how am I going to put those things together in a single assembly? What you can do, you can insert parts of assembly as you usually do, but instead of picking things from the current document, you can go to other documents, go to your on shape, and you probably have you probably have your stuff stored somewhere. Maybe you don't. For the sake of example, I'll try importing something. So what you'll have to do, I already created a version, so it might look a bit different on your end, but you'll probably see an option to create a version. And you'll want to do that because Onshape has this whole system with like version control, making sure multiple people who collaborate are able to actually work together without overwriting each other's stuff. So you have to create a version. This stuff is more if you're working with someone else, you need to be clear. If you're just working with your own things and you're not going to come back to the project, maybe it's very fast. Just create it. And once you give it a moment, it'll create that version. And so now you'll be able to access the other assemblies in your other documents. So let's say I want to insert assembly 1. So this whole assembly, that was not contained at all within this document. All I had in this document, I created it brand new from scratch, and all I had in it was this thing. But now in this assembly, I was able to import this because I had made this before in a different document. And what you can do, let's say that I saved that, I finished working on that document for now, and I will go to this document. And let's say that I go into here and I make some changes, like maybe I make another gearbox, I change the wheels out, I change the motor out, and I do all these changes. When you go back, it might be the case that this assembly doesn't update. So I might have like changed the wheels out, but here it still looks the same. What you can do is just go to assembly, and if you update the link document, in this case, I didn't actually change it, so there isn't a newer version available. But if I had, I would have been able to update this. And that's kind of how like the whole version control thing works. Just make sure that everyone has, or at least everyone knows what version of files everyone else has been working with. I'm sure most of you have probably gotten past this or figured something out yourselves, since most of you have, I assume, assembled something. So if that was a problem that was affecting you and you just didn't want to say something, well, now you know. So if there are any questions about that, feel free to ask. If not, I'll move on. All right. So kind of the third thing I want to show you is like the public part of Onshape. So by default, the stuff that you make here, I believe is set to private, but you're able to make it public. And if you do, like pretty much everyone who uses Onshape will be able to see the thing that you like publish. So these are all things that someone else has made and they published it. And as a result, I'm able to see it. I'm able to open it. You can kind of search for things that you want. Let's say I want a bolt. It's not a great resource perhaps, but if you're just curious, it's kind of like Grab CAD in that it's a community of people who I guess enjoy CAD, and you can kind of look around, get inspired. If you can see what other people think about robots. Yeah, so what you'll get here is kind of like a sense of the fact that there are other people using Onshape and people are doing all kinds of things with the program. See some cute robots here. And so that's that. That's something that you can explore with, kind of like you did with GrabCAD or similar forums. What's a bit more relevant maybe is if you want to share a CAD that you made with someone else, the first way to do it is obviously, as we talked about before, you can just export your files and you can save the physical like file onto your computer. So there's STL for 3D printing. There's like STEP and IGES, Parasolid, which are very common. If you know someone who uses SolidWorks, of course. So you can just like send them the actual file, maybe like an email or server or flash drive. Another way you can do it entirely through Onshape if the person you're sending it to uses Onshape is you can click that share button in the top corner. And one thing you can do is link sharing. It's kind of like Google Docs if you're familiar with that. The other thing you can do is make it public. So this one I already made public. You can see that this document is public. If you start on a document that's not, it'll provide you the option to make it public. And so the way, I probably shared documents with you before. This is a sensor. As we talked about last week, your robot needs to be able to detect where it is. Well, not your robot per se, but in general, robots need to detect where they are. And so this is a kind of a lever-based touch sensor. It's very simple. Fundamentally, there's just a button here, and this lever kind of extends its reach. So if anything touches against this lever, it'll press the button, and the sensor is able to detect whether or not that button is pressed. But if you have a public document like that, what you can do is just copy that link as I did there in the URL bar, and I just put that into the chat. If you click on that on your own Onshape, what you'll be able to do is open it up and like use it for yourself. And it's kind of the power of a public document. I just gave that to you, so if you want to use this like lever button sensor, feel free. You can import that into your own CAD. Maybe, let's see if I still have a model. All right, so at this point, you probably have more or less an assembled robot. Something along the lines of a frame with wheels and an arm in the middle. And so what you can do if you open that document, you can make a copy to save it onto your own Onshape, and then you're free to import it just like I did, like that. I guess what you'll observe is that this model was not completely fixed to itself. So what you could do to resolve that is well, the first thing you could do is like download it as an STL and then re-upload it, because as you recall, when you import files, it kind of gives you the option to combine all the bodies into a single component. Other thing you could do is just like mate them in place as they are. Let me illustrate what I'm talking about. Yeah, so I could just export it by right-clicking this here. I'll just put that in my downloads. And it's kind of what we're talking about when we like get CAD from other places. Sometimes like the CAD will be broken, sometimes it's not assembled the way you expect. So you kind of need to like think to yourself like what you're going to do about it. In this case, I can just combine everything into a single, well, I can import to this document and then I'll tick this box that says create a composite part. And having done that, we can see now that this whole thing is just a single body. And when I return, I'm able to is that four? That's four. Yeah, I'm able to insert these sensors into this new assembly. And what I can do now is just mate things to my chassis. And so if you wanted sensors on your robot, you can always find your own sensors. This one in particular was modeled by, I think, one of my classmates, former classmates. But this was modeled after like a real sensor that we had access to for a class. If you're interested in other sensors, you can go to like a catalog. So just like we had McMaster for like hardware parts, maybe like DigiKey is a common there's also like Rev Robotics, as we talked about. The thing is that for like sensors, it's not really like McMaster where almost everything has a CAD model. You can select things like here and search for things with CAD models, but it'll often be the case that you have to model things yourself. And so in those cases, what you can do is just like we did when we were modeling the arm and the gearboxes, you can just kind of like look at the part yourself and just make a standard model like we did here for the motor or here for all of these servos. Like what you should always ask yourself is like, do I need an accurate model of this? And like, what is this model being used for? And in most cases, since you're not actually like building the servo yourself, you're buying it off, like you're buying it. And so you know that the part is going to have whatever geometry it has, regardless of how you model it. And so as long as you have something that's suitable, like it has a similar bounding box, it'll take up the same amount of space, then that's probably what you should do for most like sensors. So like this is one we talked about earlier in this class. I'm sure they have plenty of sensors. And so if you're so inclined, if you want like this color sensor, you could try like CADing this yourself. You can see like it's kind of a rectangle with the corners chamfered off. And then there's this little rounded tab here with a hole in it. Yeah, so that's pretty much it for the demonstration parts. If you have any questions, feel free to ask. I did receive another question. So again, like anonymously, we will, I guess this one's kind of also applicable to many people, perhaps. And the question is like, essentially, like, does it matter what color I made my parts? And the answer is no. Like, everything up to this point has been your free choice. You're free. For those of you who want a refresher, like, if you go to a single part, you can go here and you can edit the appearance. And so perhaps you like black. There are black 80/20 beams that they have this coating on them. So this might actually be realistic. Also keep in mind as you like take your screenshots, maybe you don't want the default like CAD views. So make sure to hide your planes and origin. You can do things like, as I mentioned before, like perspective. Maybe like something like that. It's really all up to you. Like if it's an aesthetic thing or even a design thing, in general, you don't have to ask. The answer is probably yes. But yeah, we're coming up close to 7 o'clock. So if there are any last questions before the class ends, now's the time. As a reminder, just next week, aim to have everything done by that class. If you run into any unexpected problems, don't stress out about it too much. Just be prepared to work on it with Jack, who'll be there next week. And after like that first part, you should be pretty much ready. We'll have our presentation for most of the class and you'll be able to see everyone's robots. I'm pretty excited for it. I hope you're all excited for it. You put in a lot of work throughout the last 7 weeks. And so hopefully it's a good way for you to kind of celebrate what you've done and have a strong finish to the CAD that you've learned and the mechanical design that you've learned throughout this class. Yeah, and with that, we're just a minute short, but I have nothing more to say. So yeah, you're free to go. Class is over. See you all next week. Or I guess Jack will see you all next week.
Bye. Bye.
Bye. Thank you so much.